Hi, let's talk about the sensory systems of the body. In this chapter, we'll talk about the different kinds of touch sensation. We'll talk about hearing and vision and how those are integrated into motor action. So, at each organism, whatever they have the ability to detect in the environment has a lot to do with their evolution and what has been selected for by natural selection. For example, we as primates have excellent vision, we have excellent three-dimensional depth perception, great color vision compared to other animals, but our sense of smell is quite poor. Mice and dogs have excellent sense of smell compared to humans. And the example that your textbook uses is the star mole, which is almost completely blind, and but instead has a nose that has the ability to sense touch in a way that almost no other mammal has. And that's because of their environment and where they live. So these star moles are detecting their prey, which mostly consist of small insects, beetle grubs, worms, things like that. They're detecting them by touch. They spend a lot of time digging, and that's why they're almost blind. Vision is not needed or important to them, so they have lost it during the course of natural selection. Vision is expensive energetically, so if you don't need it, it's better to get rid of it. Um, and it has a brain and it integrates the sensory input and coordinates that into a motor output, such as grabbing and eating its prey. So sensory input is coming in through afferent neurons. It is integrated in the central nervous system, whether that's in the brain or just in the spinal cord, in the case of spinal reflexes, which we'll talk about. And then motor output could be voluntary or involuntary motor output. So sensory reception, this means the detection of something in the environment. And sensory reception, we could be talking about sensing the osmolarity of our blood, sensing light, sensing heat or cold with our fingertips. That's sensory reception. That is going to be turned into an action potential. That's transduction. So if the signal is strong enough and is detected by the correct receptor that can detect it, it will be transduced into an action potential. Then that action potential will be transmitted to the central nervous system. That's transmission. And then perception is what the central nervous system detects or interprets from that action potential. So the central nervous system is not detecting whatever it is in the environment directly. The central nervous system is reconstructing what it thinks that input was based on just getting action potentials from afferent neurons. So how it is sometimes our central nervous system interprets that information incorrectly because it's not detecting it directly. So the reception, it can take place both of external stimuli like light or sounds, or internal things like the pH of our blood or the osmolarity of our blood. We also have sensory receptors for those things. The sensory receptor could be the neuron itself. Some of the sensory receptors that we have are just naked dendrites of sensory neurons, and they react directly. In other cases, there is a cell that is the receptor cell, like the hair cells in the cochlea of the inner ear, that are detecting sound, and they are communicating with the afferent neuron through a synapse and sending the signal to the central nervous system that way. So we have both types uh, of these sensory systems. Some are specialized cells that detect a stimulus and then send that message on to an afferent neuron, and sometimes it's the afferent neurons directly. So transduction, sensory transduction, is taking that stimulus and turning it into a change in the membrane potential of a receptor cell or the neuron, if it's the neuron itself is the sensory cell. And it may not result in an action potential. So these are graded potentials. When we talked about neurons, we talked about how different signals can be additive and they may not add up to an action potential. They may be polarizing or depolarizing. If they're polarizing, they might eventually add up to be an action potential, or a strong enough stimulus might result in an action potential. So, and then this signal, this is how the central nervous system is going to be assisted in figuring out how strong the stimulus is, because an action potential, if you remember, is all or nothing. So it doesn't have different strengths, right? An action potential has one height, right? It's just it's a one kind of depolarization. So the way the central nervous system can determine how strong a stimulus is by the number of action potentials. So a very strong stimulus will generate many, many action potentials close together, or they might also be coming in from multiple neurons at near the same site. And that's how the central nervous system can tell whether a signal is strong or weak. So, and some sensory neurons send off action potentials regularly. That's how they are on. And so the way that the central nervous system can determine if there's actually a signal is by the number of action potentials. High frequency of action potentials would indicate a stronger signal, because every action potential is exactly the same height, if you want to think of it that way, or strength, because an action potential is all or nothing. Once it's triggered, that triggers it to reverse as well because of those voltage gated potassium channels. So an action potential has one height. So the strength of the signal has to do with the number of nerves sending, or neurons sending, the same signal from the same location, and also the frequency of those action potentials from each neuron. So that signal then goes to the central nervous system, where there could be a motor response to that. There could be no action taken, and the sensory input may also be completely ignored, depending on what it is. And that is the perception. So the perception is what the brain interprets from those action potentials. Because remember, the brain is not sensing whatever it is directly. The brain is deciding what is happening based on which nerves are bringing the signal. So different types of receptors send different types of signals. And that's how the brain is deciding, okay, it's an action potential that's coming from the cochlea, so it's a sound. It's an action potential coming from a pain receptor, so it's pain. It's something that I want to avoid. So that's how the brain is deciding what the stimulus is by which neuron that signal is coming in on. And this is where perceptions can sometimes be incorrect, is because the brain is not detecting things directly. And inflammation, as we'll find out, can sometimes cause increased pain perception when there's not actually an increase in stimulus of pain. So signals that, as they are coming into the central nervous system, can be amplified so that they seem greater than the stimulus actually was, or they can be ignored by a process that we call sensory adaptation. And sensory receptors themselves can become less likely to generate an action potential to repeated stimulation. And we see this all the time with touch, that if you wear the same thing all the time, like if you wear a watch every day, the first couple of days you might find it kind of annoying. Or if you're just starting to wear contacts, the first few days that you're wearing the contacts, you find the contacts annoying. You're constantly thinking about the fact that you have these contact lenses in. But after a while, you don't feel them anymore. You get used to it. That's sensory adaptation. That means that the neurons themselves, in many cases, are not even responding anymore to the stimulus. And in some cases, like becoming used to traffic noise, it's the central nervous system that is now ignoring the input of a particular type because it says, oh, that doesn't mean anything. That's insignificant. I hear that all the time. I don't even want to, I'm not even going to pay any attention to that whatsoever. So that's two types of sensory adaptation. Either the neurons themselves are no longer going to send an action potential, or the central nervous system will ignore the signal from the sensory neurons. Both of those are sensory adaptation, decreased responsiveness to repeated stimulation. So there are 5 basic types of sensory receptors, and we have examples of all of these. Although there are types of these receptors that humans and other mammals like us don't have. Mechanoreceptors, and we're talking about examples of all of these. Chemoreceptors. Mechanoreceptor is something that responds to an actual deformation of the cell. Cilia get deformed, or pressure. Something is changing, mechanically changing the shape of the cell, and that's what it's responding to. Chemoreceptors are detecting particular molecules. Our sense of smell is an example of that one. Electromagnetic receptors, the electromagnetic spectrum includes light. So we could definitely detect, we have electromagnetic receptors in our retina. Thermoreceptors, this would be detecting changes in temperature, and we have thermoreceptors for both hot and cold. And then pain receptors are nociceptors, and pain receptors are different than the other types of receptors. Pain receptors can respond to a wide variety of inputs. So pain receptors in your hand can respond to both heat and pressure, and they will fire in different cases. So pain receptors are kind of unique, and have evolved by natural selection to get us to avoid things that will injure our bodies. So they're kind of special in that regards. So mechanoreceptors are responding to physical deformation of the cell itself. So it's either being squashed by pressure on your fingertips, or it's hair cell. Well, they're called hairs. They're not actually hairs. They're cilia in the cochlea of the ear being moved by sound in the fluid of the cochlea, and that will generate an action potential. So those are types of mechanoreceptors. So let's look at skin here. So this is a close-up of a little slice of skin here. We have the non-living layers of the epidermis on the outside here. So we're not going to have any sensory receptors in that layer. They're going to be below that in the living layers of the skin. And we have several different types. We can detect gentle pressure and also deep pressure. Those are separate types of receptors. The deep pressure receptors are not activated by gentle touch. And so sometimes you can lose one and not the other. We also have the ability to detect when hairs anywhere on our body are moved or are either by touch or by wind, for example. We can feel that. And we also have pain receptors that are naked dendrites. Chemoreceptors respond to specific molecules. Sometimes they respond to general types of change, like change in pH or change in osmolarity. And sometimes they are detecting specific molecules, like for our sense of smell, we're detecting specific molecules that bind to receptors. So if you smell smoke versus if you smell vanilla, there's different receptors that are binding to the molecules there that you're breathing. And that's why you smell those things as being different. We have as I said, humans don't have a particularly great sense of smell. One of the best senses of smell, if you want to think of it that way, are moths that can detect pheromones. They can detect a single molecule of pheromone and that will send a signal to their brain and head them in that direction. And this will be only the males. The females are producing the hormone, the males are detecting the hormone. So if you see a moth that has these huge feather-like fluffy antennae, which increases the surface area for receptors, then it's a male. Electromagnetic receptors. There are several different types. Any organism that can detect light, that is an electromagnetic receptor. And many, in fact, I would say most animals have some ability to detect light. At least, even if they don't have real eyes, they at least can detect whether it's day or night. Even jellyfish can do that. And then there's a few others, a minority of animals that can detect electrical signals and magnetism of the earth. For example, one mammal that can do that, this might be the only mammal that can do it. The platypus, duck-billed platypus, is weird in a lot of ways besides being an egg-laying mammal. And the only poisonous, or I shouldn't say poisonous, the only venomous mammal, it also is the only one that can detect electrical signals because it hunts fish in murky water, so they can detect the electrical signal from the fish's nervous system. And there are a lot of fish that do this as well, including sharks, can detect the electrical signal made by other organisms' nervous systems and use that to find them and bite them, even in very murky or dark conditions. Detecting the magnetic field of the Earth, this has been speculated about for 100 years, and it's only been definitively proven in the last few decades. How homing pigeons find their way back to their home base has been speculated about for a long time. We still think that homing pigeons are using more than just the Earth's magnetic field. Other migrating birds have also been shown to use the Earth's magnetic field to migrate. Like swallows use the Earth's magnetic field to migrate. It's been known for a long time that homing pigeons get lost in particular areas, and it's been shown in the last few decades that there's one area in Pennsylvania where homing pigeons always get lost and end up on the ground in people's yards, and it turns out it's a magnetic anomaly. So it screws them up if they fly over it because there's a lava dome or something that's buried there from an ancient volcano that creates a magnetic anomaly in the area. So how do they do it? How do birds detect Earth's magnetic field? Well, we know that one element that can react with the magnetic field is, of course, iron. And it turns out that all the organisms that we know of that can detect the Earth's magnetic field, including bees, have specific cells in their brain that have little chunks of iron in them that moves in response to the Earth's magnetic field. So it's very cool. And humans cannot respond to Earth's magnetic field. There aren't any mammals that can detect the magnetic field that have been shown, although there are some humans that claim they can do it, but don't believe them. They're like the breatharians. There are whales are also thought to detect Earth's magnetic field. Another type of radiation would be heat. Infrared radiation is heat. We can detect it with our hands, as we'll talk about thermoreceptors. If somebody has been using the stove, or let's say there's a pot of food on your stove, you just got home and you don't know if it's hot or not. How do you tell if it's hot? You don't even have to touch it. You can just hold your hand near it and feel that it's hot. That's detecting infrared radiation. Some animals are really good at detecting infrared radiation, like some snakes have a special organ that is really good at giving them directionality for sensing radiation, and they use this, of course, to find their warm-blooded prey. But we can do it too. We don't do it with our eyes or with our face, but we can detect um, infrared radiation with specific thermoreceptors in our hands. We actually have them all over our body, but we have more of them in our fingers. which is why it's easier to tell if something is hot using your hands. You don't even have to touch it, you just have to get near it. And we also, though, can detect if things are cold. And you might imagine this has been selected for by natural selection, and not just mammals have this ability, but reptiles as well. Remember, many reptiles are not endothermic, and they need to find a warm rock to lay on or know when they're in the sun to tell this is a good place for me to lay to warm up. So for reptiles, this is also really important. Our thermoreceptors can be fooled. There are certain molecules made by plants that can fool our thermoreceptors. The reason that hot peppers are hot is because of a molecule called capsaicin that they make, and we talked about this a little bit with when we talked about plants, that capsaicin affects insects and also kills fungus. And so plants are making this for a specific reason, but it also deters mammals from eating their seeds. That's where most of the heat is. And because it stimulates both thermoreceptors and pain receptors. Now here's a case of pain receptors being recruited in when the thermoreceptors are highly stimulated. And it's because it stimulates an action potential in the thermoreceptors, and your brain is interpreting or perceiving that sensory input based on which neuron it's coming from. So the neurons that detect heat are sending the action potential, so that tells your brain this is hot. And then eventually when the nociceptors get recruited in, because there's so much stimulation, then that tells your brain, I am getting tissue damage, I am being burned, this is hot, it's burning me, it's painful. But there isn't any tissue damage occurring. Our brain is being fooled by this. And the same thing happens, but not in a painful way, with menthol. Menthol is an oil produced by mint plants. There's a couple of related mints, and it stimulates cool receptors and gives us a similar response. And that's much harder to feel on our skin, because it doesn't really get into our skin through the surface of your skin. The same with hot peppers. You can have hot peppers on your hands and you don't really feel it because the capsaicin can't get to the receptor. It doesn't go through your skin. But if you put it in your mouth, now we have a wet mucous membrane with a much thinner surface layer, and now the capsaicin or the menthol can actually get to the thermoreceptor and stimulate the sensation of cool or heat. That's why so often if you cut up peppers, you don't even know that you have capsaicin on your hand until you rub your eye, and then that is not good. Pain receptors are also called nociceptors. It's from the same Latin root as the word noxious. So you could think of it as a noxious stimuli. So nociceptors get involved when the other receptors are really highly stimulated. They are designed to keep us from injuring ourselves. And you may know that there is a very, very rare genetic condition where people simply don't possess nociceptors at all. They can't sense pain at all. And they rarely live through childhood because they don't avoid things that are harmful. So nociceptors will respond to high heat, high pressure, even chemicals. They are inflamed when there's inflammation or injury in the tissue, and they will be more likely to send off an action potential if there's inflammation. So for example, if you cut your hand and then it swells up and you get a little infection and now it's all red and swollen, it's going to be very painful. Just a slight touch is going to be very painful. That's because the nociceptors are much more likely to send off an action potential when there's inflammation. And prostaglandins are part of that process, as we talked about in a previous chapter. And I think that was in the immune system chapter. that prostaglandins enhance inflammation and our sensation of pain. And that's how ibuprofen works. So Advil and Motrin and aspirin work because they lower the synthesis of prostaglandins. For most animals, hearing and the sense of balance or equilibrium. So equilibrium includes where you are in space, which way is detecting where you are in gravity. So which way is up. That's part of equilibrium. And for mammals and reptiles, hearing and equilibrium are connected, but not for all animals. Insects, as we'll see, these are separate senses that are in different places in the body. So for invertebrates, they often use something called a statocyst, which is a little ball of cells that have cilia. And again, this is going to be a mechanoreceptor because it's detecting the movement of these cilia based on these little statoliths bumping around inside the statocyst and bumping into them. And where have we heard before, way at the beginning of the semester, about little statoliths being used to detect gravity? And in fact, that was in plants, if you remember, that roots and shoots detect which way is down and which way is up based on statoliths moving around. So the same thing can be invented and used more than once by natural selection. And so that would be an example of convergent evolution, because the ancestor, the common ancestor of plants and animals, didn't have statoliths. So in insects, they have these small organs inside their body that have cilia pointing inwards and little statoliths, which could be made out of calcium or some kind of mineral. And then as they tip, the little statoliths would move around, and wherever they're deforming the cilia, that would tell them which way is down. So very simple kind of proprioception, which way their body is positioned in gravity. Not all insects could hear very well. Most of them just use the hairs on their body to detect sound. So that's not a great system. So that means that most insects can't hear very well. They can hear, but not, they're not, unless they're using it for communication. So many insects communicate with one another with sound. In that case, those insects, like crickets, this is a cricket, they have evolved specialized organs to give them much better hearing. In fact, it's somewhat similar to what evolved in reptiles and mammals for hearing, and that is to have a thin membrane stretched over an air pocket, kind of like a drum, which is why it's called a tympanic membrane. Which greatly enhances their ability to hear sound. Crickets, well, male crickets chirp, and they chirp for two reasons. They chirp to attract females, and they also chirp to ward off other males out of their territory. For mammals, and well, also for reptiles, hearing and equilibrium and movement are important and are in the same organs, both in the ears. And so that's what we're going to talk about in the next video. We'll talk about how mammal hearing works, and also we'll talk about vision.